In this video, I'm going to talk about IEEE 802.11 standards. The 802.11 standard defines the mechanisms that devices can use to communicate wirelessly with each other. Through 802.11, RF signals, modulation, coding, bands and channels, and also data rates all come together to provide a robust communication medium. Since the original IEEE 802.11 standard was published in 1997, there have been many amendments added to it. The amendments cover almost every conceivable aspect of wireless LAN communication, including things like quality of service, QoS, security, RF measurement, wireless management, more efficiency or more efficient mobility, and ever increasing throughput. By now, most of the amendments have been rolled up into the overall 802.11 standard and no longer stand alone. Even so, the amendments may live on and be recognized in the industry by their original task group names. For example, the 802.11b amendment was approved in 1999, was rolled up into 802.11 in 2007, but is still recognized by its name today. When you shop for wireless LAN devices, you will often find the 802.11a, b, g, and n amendment listed in the specification. The first standard is 802.11 1997. The original 802.11 standard was ratified in 1997. It included two main transmission types, as you can see here, FHSS and DSSS. Okay, and for use only in the 2.4 gigahertz band, the theoretical data rate include 1 and 2 megabit per second, as you can see here. I explained them in previous video, but let me to review it. Band 2.4 gigahertz, transmission type FHSS and DSSS, and you know that in FHSS we can reach to the for example, data rate of 1 and 2 megabit per second. With DSSS, with DBPSK, we can reach to the data rate of 1 megabit per second, and with DQPSK we can reach to the 2 megabit per second. Actually, here we have the different modulation type, and in the differentiated quadrature we reach to the 2 megabit per second in compared with the differentiated binary. Because of that, as we can say in the original standard 802.11 1997, the maximum speed or the maximum data rate is 2 megabit per second. Now let me to explain a little about the 802.11b. To increase throughput over the original 802.11 1997 standard, 802.11b was introduced in 1999. It offered data rate of 5.5 and 11 megabit per second through the use of complementary code king or CCK, as I explained before. Because 802.11b was based on DSSS and was used in the 2.4 gigahertz band, it was backward compatible with the original standard. Devices could select either 1, 2, 5.5 or 11 megabit per second by simply changing the modulation and coding scheme. This table lists the new data rate introduced in the 802.11b. As you can see, it works only on the 2.4 gigahertz band. Transmission type is DSSS, and about the modulation, we have DQPSK with CCK, and data rate can be 5.5 and 11, but don't forget it is backward compatible with the original standard. Because of that, it supports 1, 2, and then 5.5 and also 11 megabit per second. The next standard is the 802.11g. With 802.11b, the DSSS maximum data rate was limited to 11 megabit per second. To increase data rate further, a different transmission type was needed. The 802.11g amendment was based on OFDM and was introduced in 2003. It is commonly called extended rate PHY or ERP. Extended rate PHY or ERP, okay, or ERP OFDM. Whenever you see ERP, think of 802 to the 11G in the 2.4 GHz band. This table lists the data rate available with 802 to the 11G. As you can see, the band again is 2.4 GHz. Transmission type is ERP OFDM, and about the modulation, we have several modulation types: BPSK 1/2, BPSK 3/4, QPSK 1/2, QPSK 3/4, and then 16 QAM 1/2, 16 QAM 3/4, and 64 QAM 2/3, and 64 QAM 3/4. As you can see, data rate increases from 6 megabit per second to 9 megabit per second, 12 megabit per second, 18 megabit per second, 24 megabit per second, 36 megabit per second, 48 megabit per second, and finally 54 megabit per second. Actually, by selecting one of the 8 different modulation schemes, wireless devices can choose data rate of 6, 9, 12, 18, 24, 36, 48, or 54 megabit per second. The higher data rate can be used when the signal strength and signal to noise ratio SNR are optimal. Clearly, 802 to 11G offers for superior throughput than 802 to 11B. It might seem logical to simply use 802 to 11G and its higher data rate everywhere. Sometimes that is not possible because 802 to 11B only devices are still being used on a wireless LAN. Notice that the 802 to 11G and 802 to 11B use completely different transmission types, OFDM versus DSSS. This means that 802 to 11G and 802 to 11B devices cannot communicate directly because they cannot understand each other's RF signal. Oddly enough, 802.11g was designed to be backward compatible with legacy 802.11b devices. Devices using 802.11g and OFDM are able to downgrade and understand 802.11b DSSS messages. However, the reverse is not true. 802.11b devices are limited to DSSS, so they are not able to understand any OFDM data. When two 802.11g devices are communicating with OFDM, 802.11b devices cannot understand any of the transmission, so they might interrupt with transmissions of their own. To allow both OFDM and DSSS devices to coexist on a wireless LAN, 802.11g offers a protection mechanism. The idea is to precede each 802.11g OFDM transmission with DSSS flag that 802.11b devices can understand. This figure compared the basic sequence of event as data is transmitted in a native 802.11g OFDM network and when the 802.11g protection mechanism is enabled. When an 802.11g device is ready to transmit data in protection mode, it first sends a request to send or RTS and a clear to send CTS message using DSSS and a low data rate, that informs all 802.11b devices that an OFDM transmission will follow. Any 802.11b devices that are listening must wait for a predefined time until the transmission is complete because the OFDM transmission is unintelligible. Protection mode is enforced if an 802.11b device is detected on a wireless LAN. If the 802.11b device leaves the local network, protection mode is lifted. While the protection mechanism enables 802.11b and 802.11g devices to share the wireless medium, it also reduces throughput significantly, often by 1/2 or more. To get the most performance out of an 802.11g network, you should make sure that there are no 802.11b only devices in use. Be aware that 802.11g has the following limitation. It is used in the 2.4 GHz band, which offers only 3 non-overlapping channels 1, 6, and 11. OFDM devices are limited to a maximum transmit power of 15 dBm rather than the 20 dBm with the DSSS. This is due to the way the RF energy is spread across the channel widths. The next standard is the 802.11a. Both 802.11b and 802.11g share one problem. They live in the 2.4 GHz ISM